So let me see what time it is. It's time to get started. Okay, so this is again where I'm doing my edits, and everything prior to this will be remote in my final edits. So look at this. It is lecture ID 10. That's honestly a little bit hard to believe because we just started and now it's already lecture number 10. So it seems that the course is pretty much done. It's still some few matters to discuss. And honestly, I think that I'm a little bit behind the schedule, and I don't think that I'm able to close the discussion about the hydraulics today. I don't think so because we still need to discuss about the flow types, and then we can start looking at the different components. And we that different components will take a little bit of time. So we need to look at the little throttle valve, restriction valve, direction valves, different types a little bit, pressure relief valve, cylinder pump. Those are the components we're gonna take a look. And and I'm kind of this is my prediction that we may be able to cover direction valve, pressure relief valve will be mostly reading assignment. Cylinder, I think we're able to do that, but the pump is quite a bit of the things to discuss. So probably unable to do that today. And we'll continue from that topic next Monday. And next Monday, we're gonna discuss about static analysis and mainly about the flexible bodies. And then what happens is the best lecture in this class. So the best lecture in this class is real-time simulation games. That's what I like. Personally, I like that the most. And that will be the last one. And then there will be one more lecture. The lecture ID 13. 13 is a summary from the material that you're expecting or you will see in the next midterm exam. So the next midterm exam started from the lecture number 8 from that on. So what are the things that make sense to know prior to entering the midterm exam? So that will be lecture ID 13. That's it. Another thing that we need to discuss, I think we need to do this kind of like a voting action perhaps next Monday. And that's going to be how is it we going to have the next midterm exam? Because I think we can have the midterm exam a little bit earlier than officially announced. Officially, I think it is announced to be, I think, a second week of December. But we can have it earlier if that's what you want. Or we can have it later if that's what you want. I kind of recommend it to have it right after the lecture number 13. So as soon as we're done with the lecture number 13, the next week would be the second midterm exam. That's what I'm proposing. But that's something we can discuss in today's team. And also I can organize a voting action through the doodle or some other stuff. So we'll see how it goes. But I think we need to reschedule a little bit about this second midterm exam. Okay. Now let's move on. So first summary what we discussed last week. So last week we discussed shortly about what are the fluid properties. And we concluded that modeling wise, there are two properties that are important for us. There's viscosity, which is not that important, and the bulk modulus, which is very important for us. Viscosity, why that is not so important? That's simply because viscosity is needed in certain laminar flows. And like I explained you last time, laminar flow takes place when the pressure difference is small. That's usually not the case when we are speaking about industrial applications, particularly when we are speaking about applications of mobile machinery. Bulk modulus, that is extremely important. Bulk modulus defines how is the flexibility of fluid. And the fluid is flexible. That's something that is very important to understand. In practical life, the flexibility of fluid is sometimes more significant than the flexibility that comes from the mechanical components. And the flexibility can be computed by first accounting the flexibility of fluid itself. And modeling wise, we're going to use something that is called effective bulk modulus. effective bulk modulus effectively takes all the flexibility component or flexible components into account. And these flexible components are, like mentioned earlier, is the flexibility of fluid itself and the flexibility of containers. The flexibility of containers in practical life varies quite a bit. There are hoses, rubber-made hoses, where there is some steel net. Those are capable to introduce some significant flexibility to the system. And then on the other hand, like steel pipes, cylinders, their flexibility is practically insignificant. But last component you can find in this equation is related to dissolved air. That is very important. Even though that, of course, the idea of the hydraulics is to get rid of the air, it's still there in many of the practical applications. And if there's any, even a small amount of dissolved air, that's problematic in two different ways. Well, first of all, it makes system to be vulnerable for cavitation. So the cavitation can take a place in a certain components, and then it lowers the flexibility. And as a rule of thumb, we would like to make everything, mechanical components, hydraulic actuators, and so on and so forth, to be as rigid as possible. Okay, this is what you need in this week, last week, weekly homework. So in last week weekly homework, there was a simple hydraulic-driven crane, and it was asked how is a natural frequency, lowest natural frequency of the structure. And in that particular case, the flexibility is assumed to become from the hydraulic cylinder only. You can, the natural frequency, you can, of course, compute it as a square root of stiffness divided by mass. So that's an equation you need. And mass, you can get it from the assignment itself, and the stiffness you can compute it by using this equation shown here below. Yeah, this is an effective bulk modulus which we're expecting you to estimate. Whatever is that means that that you can use the lecture material, you can make an assumption, and that's what we're expecting you to figure it out. And rest is just a matter of substitution. Once you do the substitution, then you can figure it out. What is the natural frequency of the crane asked? Then last week we opened a topic that is extremely important and will be asked, for sure will be asked in second midterm exam, and that is lamp fluid theory. The idea of the lamp fluid theory is to divide your hydraulic circuit within the volumes where the pressure is assumed to be equally distributed. So what that means, we will take a look at an example in a second, but just for your information, we're going to kind of discretize our hydraulic circuit to certain volumes. And within these volumes, the pressure will be computed by using first order differential equation. And the first order differential equation is this. So this is a P dot. And, like in mechanics, once we have Q dot dot, we can get Q dot by means of integration, and a Q in the means of integration. Similar way, from P dot, we can get the P. P, in turn, is what we are after, because we would like to know how much pressure is applying in a different part of the hydraulic circuit, because eventually we would like to estimate how much is a pressure in hydraulic actuators. And actuators are, well, the most often used is, of course, hydraulic cylinder. There may be a motor too, but the information you need is definitely pressure. And the response to that is that the green screen is still missing. It's in a mail. I ordered, but I didn't get it yet. But it will be here in my home office. I'm expecting, well, the delivery day is actually Thursday, this week, Thursday. So I'm expecting that to be here next Monday. And there's going to be another surprises too. So stay tuned. There will be some nice surprises, hopefully nice surprises. Okay, back to hydraulics. Back to the hydraulics. What is that we have in this first order differential equation? ingredients, components here are effective bulk modulus. That is a description of flexibility. So soon there will be a question about what this fluid fluid theory ignores. So one of the options is a flexibility. It's not ignoring that because flexibility, as you can see, is in this equation. Volume size is here. The volume can change its size. That is particularly the case in the hydraulic cylinders, and that is accounted as well. Then there is these two guys in the middle, which is a flow rate in, flow rate out. So the pressure is a function of flow rate, which makes sense, of course, and the change of the volume itself. So those are the components you need to compute the P dot. P dot, remember, is not the P, but it's related to P, and you can get the P in terms of time integration scheme. So that's how it goes. So here's an example. So last week we looked at the damper. So we looked at the simple fluid damper, and we concluded that the damper can be modeled in such a way that we can compute the pressure here in this side of the piston. This is the same volume. And now what I mean about dividing hydraulic circuit within the volumes where the pressure is assumed to be equally distributed. It means that here, this area can be considered as a one volume, meaning that the pressure, say, this corner is exactly the same as the pressure in this corner. And that is the case. There are, however, in the practical cases when we're using line fluid theory, we're making a little bit of, we kind of cutting the corners a little bit because, when we have a long pipelines, the long pipelines will introduce certain amount of pressure losses. And that's something that we do not account when using line fluid theory. Another thing we do not account is we do not take pressure waves into account. The pressure waves, which is like, traveling back and forth in the pipeline, those are the ones we ignore when using the line fluid theory. So, back into this fluid damper, I'm continuously checking the chat window as well, and that's why I'm looking a little bit like distracted. Because I'm happy to see there's some complaints and there is a temptation to give some extra points, but I cannot do that because, if I would do that, then this would go too wild, because everyone would follow the same procedure and this is not the purpose here. Back to this damper, here, this is a volume where the pressure is computed by using this differential equation. Again, flexibility is here, original size, flow rate in, flow rate out. Then the flow can travel through this drilling here. This is accounted by using these components. Depending how you're putting the positive sign, it's going to be either out or in. Well, that's a selection you can make. That you just be consistent with that and you are okay. This is a volume size, or change of the volume size, and that's okay. Now this is now assumed that the flow rate is leaving, so the only component that will be active here is this one. Then this is another volume here. Here too, we're going to use this first order differential equation to compute the pressure as a function of time. That's how it goes. Let's look at a little bit more realistic hydraulic circuit. Here is an example we looked previously. Here, we're computing the pressure in this pipeline, and this could be in practical life, a little bit a longer pipeline. And if that's the case, then we're simply making an assumption that the pipeline is not introducing significant pressure losses. That may not be exactly according to reality, but it's the best guess we can make. Also, because we have only just the one pressure, we cannot take this pressure fluctuation because of the pressure waves. We cannot take those into account. So that's the thing we're ignoring when using the line fluid there. Then we have here a throttle valve. In a throttle, there is a pressure losses, meaning that we cannot assume the pressure here to be same than pressure here. That's simply because of this component. And now, pressure here then can be assumed to be same right after the throttle valve and in this corner of the cylinder. Maybe that's not exactly according to reality, but it's close up to approximation anyways. And then in a way back, we just have one area, one volume where the pressure is compared. So that's how it goes. Let's practice a little bit, and then there is a first in class quiz for today. Actually, the first in class quiz for today is already available in Socrative, so you may log in. Let me just double check that it is. Yep, yeah, it's up and running. So you get to go. And I see that we already have some answers in the Socrative. And there is a game is on. So you guys thinking that success rate today will be 100%? We'll see. We'll see that. We'll see that. Okay. Back to this slide. Here I have a kind of like a piece of hydraulic circuit, and I'm asking you to form an equation to compute the pressure. I have here flow rating, which is a little bit small, but it's a flow rating. Then I have a pipeline that is connected to cylinder. Cylinder is a one-way cylinder, so there is a piston and no fluid in this side of the piston. And the motion of the piston is measured by using x and x dot coordinates that is measured from this coordinate respect. Okay, so how is that we can make it happen? First thing is that we have to evaluate what is the initial volume size. That's going to be somewhat easy because we need to just take the hose volume into account. So that's this one here, the volume of the hose. And then we have to take the cross-section area of the piston into account, multiplied by length x. And the x is the one that is measured here. That's going to be the volume associated to cylinder. And when putting these two components together, we will have an entire volume of the system. Effective bulk modulus, that's going to be simply, using the material we learned last time. So we have here flexibility of fluid. Then we have here entire volume size, one that is associated to cylinder, and the stiffness of the cylinder. And the same for the hose size, volume size, entire volume, and the flexibility of hose. And when doing the math, the effective bulk modulus look like this. And the last component we need is how is the change of the volume. That's going to be the cross-section area, this one here, multiplied by velocity. And then we substitute. You remember original equation is like this. This is effective bulk modulus. This is what I received from the previous slide. This is a volume size, this guy here. Then there's a flow rate in, flow rate out. There's no flow rate out. There is just a flow rate in because this is the only guy we have. And I can see that my slide is a little bit tilted. So I'm going to remove it back in a second. And then I have here the final component that is associated to, hold on, change of the volume. So this is mathematically this one. Okay. And with that, we're ready to move on to first in class quiz. First in class quiz today is lamp fluid theory ignores. And then the options are here: pressure waves within the hydraulic volumes, change of size of hydraulic volume, physical size of the hydraulic volume, compressibility, flexibility of the hydraulic volume. 4 options, one only is correct. What is correct one? We will see in after a little bit. Let me make this a bit smaller so it's easier to see how is the success rate today. And the game is on. I said that the lottery tickets are placed for 100%, 99%, 91%, and so on and so forth. What is a correct value? We're going to learn in a second. So let me see, 60. We have 60, is it 63? 63. Oh, now it's a little bit too small. Okay, 63 out of the 71. So few students are still thinking, but soon we good to go. Okay, so it's we're missing 7 students, six students. My personal guess. Okay, what about if we're gonna change the game a little bit? So if I guess correctly, the success rate, can I take 1 point off from you guys? Would that be okay? So it's like a little bit of game between you and me. How that sounds? I guess it is not a good idea. But let me see your comments. Okay, so anyways, yeah, let's keep the game simple. So if I get this correctly, there will be no consequences. But if you get it correctly, 1 extra point. Okay, so my guess today is, let me see how well you see it, 82%. So it's not so great, but we'll see. And we're back here. And I'm going to close this in 5 seconds. So 3 are still thinking. So this will be closed. 2 are thinking. Well, we got no more students. By the way, and one important observation is this. Today we have 76 students. That's a good number. So I'm expecting that each one of you that are following today's lecture will pass this course because, as mentioned in the very beginning, that's pretty much the only thing you need to do to pass this course. Follow the lectures every week and you will be fine. So I'm just missing 1 student, so hurry up. I'm gonna wrap this up very soon, so I guess that I'm gonna miss 1 student because success rate today is, what is it? 84, 80, 83, 83, 83. Oh, look at this. Look at this. My guess was this, 82, and it was 83. So I'm going to announce myself as a winner. So let me see if we have any other winners here. Hold on, I'm going to just make a brief check where the game is on. Well, there's so many answers. Oh, here. Oh, we got another 82. But 82 is okay. Actually, we could be flexible enough, so it could be. And there is still something about that my figure is too big. My face is too big. I'm going to keep it as it is, so you just need to suffer. Yeah, 1 correct answer, and that's about it. Let me just write it to myself, and then we will go. Okay, so let's continue. Flow types will be next. I promised last week teams that we're gonna discuss about this weird mechanism that is called as a tensencridity. I don't know how to pronounce that, but it's a mechanism that you see here. This is a YouTube video. Let's see if I'm able to play it for you. Yeah, it seems to work. It said that I get a little bit of noise here, so I need to put it off. So it's like two bodies that are connected together via 3 ropes. So they're like wire ropes, or I guess these are just the cables. And because of these cables, you can place these 2 bodies as the configuration you see in this video. And we discussed this in the teams, and there was a question: what is the degrees of freedom of this system? Now, degrees of freedom in this system, when we're looking this from the mathematical perspective is actually such that we have two rigid bodies, and there are spatial bodies, three-dimensional bodies. You know that the spatial body have 6 degrees of freedom, so it can move in 6 different ways. Okay, now that's a total of 12 coordinates. They are connected together via ropes. Ropes are not motion limitation. They are not motion limitation. They are acting like the system that is constrained, but seriously, they are not the motion limitation. So they are not the constraints, because they are pretty much saying that. Remember, in the very beginning, in the first lecture, there was a mechanism with the mass, spring, like this. These springs are not removing the motion possibilities. Because they don't moving the motion possibilities, theoretically, the number of degrees of freedom in this system is 12. That's how it is. But there is an argument which says that it should be 0 degrees of freedom. It could be considered as a 0 degrees of freedom because of the forces, but as a multi-body system, this consists of 12 degrees of freedom. Evidence for that is this. Look, what this guy is doing, or I don't know, this person is doing, I don't know gender of this person. Look at this. So they are moving relatively with respect to each other, as can be seen in the very beginning of the video. So there is no motion limitation, because the motion limitation limits the motion regardless of what, regardless of, how the system is initially. And that's not the case here. So there are theoretically 12 degrees of freedom, because you can move them with respect to each other. But because of this tension, that's a little bit another story. We could get back to this as a tension, system with the forces in the very last lecture if you want. So you can do a little bit of thinking by yourself, and then we'll discuss again after 3 weeks. Now finally back to the hydraulics and back to flow types. Oh, now there's so many comments that I cannot read it that much, but we'll get back to that after a break, or let's say after today's lecture. Okay, the fluid is the one that is equalizing the pressure differences. That's what it is doing. This is a little bit like chicken and egg situation, because if we're going to take a look at this setup like this, so I have here a pipeline, and in the middle of the pipeline I have a throttle valve here, and the pressure applying here is a P1, the pressure applying here is a P2. So the pressure difference can be computed simply as a P1 minus P2. Okay, so if there is a pressure difference, if these two pressures are different, let's say that the P1 is bigger than the P2, what happens is that the flow started to travel through this orifice. So it's traveled through this orifice, and is traveling to equalizing the pressure difference. So that's what it is doing. Now, once we have a flow rate, that then the pressure can be computed as a function of time, because this is what we're using to compute the pressure as a function of time. Let me write it one more time. This is flow rate in, flow rate out, and then we have this term that is describing the change of the volume. So these guys are the primary components responsible of changing the pressure. So it's meaning that because the pressure difference initially is something that this pressure is higher than this one, the flow started to travel. When the flow is traveling, then the pressure here is decreasing, and this one is increasing. And then the pressure difference is getting smaller. That's what happens. Now, when pressure difference is small, that means that if it is as a rule of thumb, less than a 5 bar, maybe less than a 3 bars, then how this flow takes place will be called laminar flow. Laminar flow is something that all the particles, remember we're speaking about the particles again. Particles are traveling with good agreement. So they are going smoothly, like, maybe I should make a bit bigger. better drawing. Let me remove this. Yep. Okay. So here's my throttle. And now in the case of laminar flow, the particles will travel with the good agreement, so they're moving like this. So there is no whirling. So they are going more or less straight path, straight curves like this. And that's the case when we're speaking about the laminar flow. Now there is something in the modeling wise that is extremely, extremely important for us. Something that is important for us is how is a pressure difference and the flow rate. How those things are, this is a flow rate, how those things are related in case of laminar flow. And in the case of laminar flow, this relation is a linear relation. Okay, how is an alternative for that? Well, when the pressure difference started to increase, now we're speaking about pressure difference that is more than 5 bars, it could be 100 bars, maybe even more than that. Then what happens is that the flow type will be turbulent flow. And in a turbulent flow, particles are no longer traveling with a good agreement, but there is a serious whirling. So there is a whirling like this, and turbulent flow look like this because of the whirling. So the flow rate as a pressure difference are no longer linearly related, but instead they are quadratically related. So this relation will be quadratic relation. Okay, so we will take a look at these in details in a minute, but this is for your information, and this is kind of the level of information you need to know when you're entering the next midterm exam. Okay, how is that you know when you have a laminar flow and when you have a turbulent flow? Well, there is a theoretical way to figure that out, and that is based on Reynolds number. I'm sure you have heard that before because they're teaching that already in, I guess they're teaching that in a junior high school. So in a Reynolds number, it is something that you can compute, and then you can compare the Reynolds number to something that is called critical Reynolds number. And now, of course, if the number is lower than the critical Reynolds number, then you can assume that the flow type is laminar. If it is bigger, you can assume that to be turbulent. In real life, it's not black and white like that. So there's a phase when it's not clear which one that it is. But typically, as a rule of thumb, when you make a drawing where this is a flow rate, this is a pressure difference. When we're speaking about turbulent flow, this relation is quadratic. So this is under the skewer one. But when you're approaching the origin of this curve, then it becomes to be straight line. And this is an area when it's converting or when it's changing from this quadratic curve to be linear curve. And this number is roughly the number of 5 parts. Okay, so I see that I have a problem in my camera. So let's see if I can fix that. For some reason, I don't get it. Like, why is that, the camera that I'm using, because I'm using this not nice camera, but the camera with that I'm usually using in Teams meetings, it have this tendency to sometimes kind of frozen, and I think it happened again. So, let me see. Oh yeah, it's not willing to cooperate with me today at all. So yeah, now it's okay. Now it's okay. Let me know if it is if it's doing that again. I mean that you don't lose much if you don't see me. Actually, you do. You do lose it quite a bit because that I want to use my hands, and maybe using your hands helps you to understand me. Maybe. Okay. Reynolds number can be computed by using this equation here. And what is it we have in this equation? So we'll have here kinematic viscosity. Kinematic viscosity is this one here. And then we have here velocity of the flow, this one here. And then we have something that is called hydraulic diameter. That's the one that is shown here. It is associated with what is the size of this throttle here where the flow have to enter. Okay, but that's something that is considered as a basic hydraulics in modeling wise. We can leave this as a little bit of less attention. But let's move on and let me ask you this. Reynolds number, what that is defining for us. Compressibility of hydraulic volume, size of the hydraulic volume, when hydraulic volume becomes small, when flow changes from laminar to turbulent. Those are the four options. And let me go back to my Socrates. Hold on. Here. It's still too many windows. So next. So please enter your answer. Because it's in a writing, it's put it in a writing in the Socrates, so I'm gonna leave you to think about it. And while you think about, hold on, I'm gonna move on. And we'll put it back to visible to you after a little while. And I will continue. Okay, this is what I mentioned in my introduction. So how is the relation between the flow rate and the pressure difference? And in laminar flow, as mentioned earlier, it is linear relation. Linear relation where there's a coefficient here which you can get from the pre-calculated tables. How are these pre-calculated tables? We will take a look at that in a second. So, but again, so we either have this linear or quadratic relation. That's something that you have to understand before you enter in the midterm exam. We do use that in a modeling wise as well. Okay, let's take a look at some pre-calculated tables. So this is what you can find from I guess engineering handbooks or something similar than that. Now, look at this. There's quite a bit of parameters here. We have flow rate and the pressure difference. Those are the major parameters we offer here. Then we have some geometrical parameters associated to how is the size of the drilling or the throttle we are looking at. This particular time we're looking at the rectangular shape throttle. I don't know how you can make something like this. I guess you cannot really make this. It's difficult to do in real life. But anyway, so we have here B, which is a length of this rectangular cross section, H of the cross section, and then the length. And the length is this one here. And using these parameters, you can substitute all the geometrical information here. Remember, this is viscosity. The viscosity is the one that affects this type of the laminar flow. Okay, what about more common throttle, like a drilling, which is a length of L. The diameter of the drilling is D, so it's a D power 4 multiplied by P divided by 128. And again, we have here the viscosity and the length. Okay, so it is what it is, but again, look at this. This relation remains linear. And linear because these are the constant values. And here are some other examples. So that's a lesson that you need to know. Linear relation. What about turbulent flow? So this is how it looks. In a turbulent flow, theoretically, you can write it as a flow rate is equal than the discharge coefficient. That depends on the case. That's something that we will put a little bit aside in a minute because we are starting to look at how you can model the different components. And the component modeling wise, it's going to be overly difficult to use something like discharge coefficient. You can get it from the measurements and you can get it from more detailed and sophisticated computing, but we are not going to use that approach. And then there's a cross section of the throttle, and then there is a density. And look at this. Under the skew root, we have the pressure difference. Just under the skew root. That is important. I'm just checking if my camera is still on. Yeah, it seems to be on. Okay, so those are the two flow types. And now what happens is that we're going to start looking at the different components, and that's where you need to know these different flow types. Because as soon as you see the characteristic curve, that you can get an idea how is a flow type. And I guess that's about it. So let's take a look how is our in-class quiz from the previous question. So let me put this back here. Okay, my guess about the success rate, 74, 74. So we're going down from the previous case a little bit, not much, but a little bit down. And why is that? Because it's getting late, and there's so many other things to think about, and maybe you're already checking out other YouTube channels, and maybe I don't know, maybe the Netflix is on, and you're distracted. That's why I'm thinking that the success rate is coming down a little bit. Okay, so well, let me see. So we have 4 students that are still thinking, and the game is on. Game is on. Let me see. Mm. So what do you think? Do we have still those 4 students in board, or are they already doing something completely different? Oh, they're in board. Oh yeah, I see that we're missing 2 students. So momentarily we're good to go. Momentarily. So I'm gonna close this in 5. Oh, there's a delay, so I shouldn't do this counter because it makes no sense to do it. Okay, let me finish I'm gonna finish my coffee, and then once I'm done with my coffee, then we will take a look. How is the success rate today? Based on the predictions, we don't do so well. So there is 100%. There is 100%, and maybe it makes sense to always vote for 100% because it can happen. Can happen. Let me see. There is several, at least more than 2. Yeah, there's quite a bit of you that are saying that it is 100%. Okay, so we are missing 1 student that we are not going to wait any longer. So success rate is. Well, I got scared. I got scared because I saw that the green bar is going all the way to end. I was like almost having a heart attack. I thought that again, it's gonna happen again, but not today, not today. But it was a close case, very close case because what is that the Reynolds number is doing for you? It is telling you when the flow is changing from laminar to turbulent. That is the case. It's nothing to do with the compressibility. The compressibility, remember, that's effective bulk modulus. Different story. Size of the hydraulic volume, that's completely incorrect. So that has nothing to do with this business. So it's almost like, okay, so it's not just a good choice. So with that, we're going to move on. So first component we're going to take a look today is a throttle valve. Very simple one. Very simple. So it's basically the one that I just draw to you. So it's going to be something that is introducing the pressure difference. Pressure difference, by the way, is the way that the hydraulics is controlled. And this is a more like general discussion, but shortly before we're jumping into throttle valve, hydraulics is typically controlled in a way that we have a pump that is producing energy. Maybe it's going to be a pump with variable displacement, and the pump is producing the energy to the system. And what happens in control components, which are direction valve and other components, you're kind of introducing the pressure losses. And that's the case that is still happening in hydraulics. So if there is a direction valve, I'm going to make a simple drawing about, sorry that this is a very low quality figure, but this is supposed to be direction valve. So basically the control based on the direction valve is by introducing the pressure losses. And that's a little bit of problem in hydraulics because you first kind of producing too much energy to your system, and then you're taking energy off using these control components like direction valves and others. But that makes no sense. And there been some thoughts like how to get rid of this kind of problematic scheme. And there is something that is called digital hydraulics helps a little bit in this regard. It definitely helps if you are able to do the digital pumps, the pumps that are producing the energy to the system when it is needed. And of course, there are different kind of controlling schemes for the pumps. Those are the ones that we're going to learn next Monday. And those are like load sensing pumps and others that are looking at whether or not the energy is needed in a system. And if it is not needed, they don't produce energy in the system. Those makes awful lot of sense. But we're not yet there, so we're going to take a look at the throttle valve first, and then we're going to move on to direction valve, the pressure relief valve, and the hydraulic cylinder. Okay, what about the different kind of valves? How is that we can model those in real life? Well, basically, there are two steps or two phases needed to model the valves. Those steps are that we first have to make a model about how is a moving component within the valves. And these moving components may be controlled by magnets, they may be controlled by mechanical stick, they may be controlled by pressure, spring, so on and so forth. But we kind of have to know how is the position of this moving component. This is a representation of pressure relief valve. So a pressure relief valve look like this. Let me try to make a drawing some kind. Okay, so it looked like this. Sorry that this is not the high quality drawing, but what I have here is a kind of like line that is connected here and line that is connected here. This usually ends up to be in a tank. This is this line here. This is this line here. And then I have here small drilling, which it's maybe a little hard to see because I'm using the black color, but let me change the color to be red here. So this is this pilot drive. The pilot drive is here, this dashed line. The pilot drive comes here and is introducing the pressure P2. And the pressure P2 is actually a little less than the P1 here because throttle that is here. Not clearly visible, but there is a throttle here that is introducing pressure loss. Anyway, so this pressure 2 is imposed to this side, and because the pressure is started to push this piston towards the spring. And there is a pre-tension in the spring, and as soon as the force, which is here P2 multiplied by corresponding cross-section area, is become to be higher than the pre-tension of the spring, this spool is started to move upright position. That is opening. And what happens in that case is that there is a kind of like a area where the flow started to travel through the valve. That would happen. Okay. Now, to be able to do this, first thing and the first step that is extremely critical is that we have to have some kind of prediction. How is the spool position? And that's what takes us like a philosophical discussion about how is a modeling of hydraulic components. We could, in theory, model the spool position such the way that is fully physics-based. Fully physics-based, meaning that we will take everything into account, including the mass of the spool, pre-tension of the spring, flow forces, pressure forces, so on and so forth. Theoretically, that's all possible. Practically, not convenient and not actually even possible, because certain parameters that are needed to make this kind of model, we simply don't have an access to those parameters. And that's not going to work out. So we just have to figure out something more sophisticated than that. But anyways, so this idea that we build a physics-based model in details, that includes friction, everything that you can find in real life, that's something that is called analytical modeling. Analytical modeling is not a very good idea because we need so many parameters that figuring out those parameters is not practically possible. Then what we could do as well is that we could measure the component. We can make a huge amount of measurements, and based on the measurements, we can build curve fitting techniques and other black box technique, neural networks perhaps, artificial intelligence-based solutions, and then we can have input-output relation. This could be one option as well, not feasible. That makes no sense to do that either because that requires so much measurements that we cannot do that in the real life. what we should do is a combination of these two extremes. So we should use analytical equations partly, and we should use the measurements partly, and we should somehow put these together. This is a method that is called semi-empirical method. And there is a worldwide famous researcher in the field of semi-empirical modeling of hydraulic components. Maybe you know this guy. He is in LUT, and his name is Heikki Handros. Look at his publication, and his publication is heavily involved with this idea to combining measurements and analytical equations. Okay, so a little bit lengthy explanation, but let me go back here. So this is, how is valve modeling, and it's explained that there is a huge effort to take all the necessary forces into account, and it makes no sense to do that. It makes no sense. So these two options that we can use is this empirical models, which is purely measurements, black boxes, if you may. That's one option. Then another option is this analytical models, which is okay too, but needs so many parameters that it becomes to be difficult to use. And then the final one is the semi-empirical models, and the idea is very, very simple. An idea is this. Manufacturers, that they're offering the characteristic curves for the components, which is based on the measurements. And now you use these characteristic curves to figure out what are these parameters needed in analytical models. And that's it in a nutshell. And that's what we're going to follow in this course as well. Okay, I guess that is quite a bit of discussion today. So let me move on. So here's an example. And we're going to look at a few things, and hopefully there's an in-class quiz coming soon, so I can get a little bit of activity to you too as well. So let me see if you're still alive, because I don't see any comments. Connection is excellent today, but no comments. Okay. So first component. First component is a throttle valve, and it's a simple drilling where the flow rate is forced to travel through. So it goes such the way that I have here. I'm assuming that there is a circular shape of throttle valve with the diameter D here. And I have here the pressure, left-hand side of the throttle and right-hand side of the throttle. So I need to take a look at that. This is a part when we, yeah, it will be. Yeah, I know that is a little bit hard. That I've been talking too much today. I know about that. I don't know why I'm feeling so talkative today. Well, I don't know. Anyways, let me just. Maybe this is a little bit painful to you, but hold on. Maybe this turned out to be okay. All right, so back to this throttle valve. So the throttle valve analytical equation can be computed like this. I have here the pressure difference under the square root. Then I have the diameter of this throttle and the discharge coefficient, which you can get from pre-calculated tables. There are many different. In this case, you can easily get it from the pre-calculated tables. But still, even getting this diameter from the throttle valve that physically looks like just a chunk of steel, and to measure it somewhere deep inside of this component may be quite a bit of challenge. So what we're going to do is that we will replace all these parameters other than the pressure difference by one parameter, and that one parameter will be called as a semi-empirical parameter, and that's how it reads. So we have here the flow rate multiplied by semi-empirical parameter, and then under the square root we have a pressure difference. How is this parameter? This is the one that can be written as this, so there is no accuracy loss here. So it's exactly the same thing. But why is that we do this? We do this because this parameter, as you will see soon, is something that you can easily get from the manufacturer's catalog. I have some hypothetical case in my next slide, but it shows that sets a light for this concept of semi-empirical modeling. Soon we're going to take a look how is a direction valve, and then you realize that this is actually a fairly handy way to model the different hydraulic components. Okay, so here's an example. So I have here characteristic curve, and in this curve I have flow rate. This is my Q, and my pressure difference. This is delta P. And the characteristic curve is provided here. So this is my curve. Characteristic curve, as you can see immediately, is a quadratic curve. So obviously, we're speaking about turbulent flow because this relation, flow, and the pressure difference is quadratic. So this is under the square root, or you can put it another way around. Q power 2 is delta P. So that's how it goes. Let me see if my camera is still on. It seems to be okay. Right, so we know that this is behaving as a turbulent flow. So what we can do then is that we can take this semi-empirical modeling approach. We can take the one point out from this curve, and this one point we can select to be from the 30 liters per minute. We, by the way, have to convert that to be SI units. And when that flow happens, then the pressure difference is 100 bars. So substituting that information, this equation, this simple equation, so this is a pressure difference, this is a flow rate, that gives you semi-empirical parameter. And then you're ready to model the system. How the model eventually look like is this. So I have here flow through this component is my semi-empirical parameter, the one that I got it from the previous slide, and then I have something that must be there, and that's sine term. Sine is a mathematical function that produces you either 1 or minus 1. So sine, if I write it here briefly, sine x is 1 if x is more than 0 or more than predefined value. Now we can set it this is 1. We can say if x is equal to 1 and minus 1 when this is if this is less than a 0. The camera is gone again. So let me put it back, and then we will continue. I guess that I need to use this camera. This is a more solid camera, so let's just use this. But now let's move on. The problem is that when I'm writing, it's moving a little bit, but I guess that is not disturbing. Not too much. Okay, so that's throttle valve. Let's moving on. And let's look at the direction valve. Direction valve is something we have the spool. Again, we have this moving component. Okay, so now there's a question. So let me go and take a look at the question. Oh, yeah. That's question is that why is that I'm using this sine function? So what is the purpose of that? So why not using pressure difference here? Well, there is something that I didn't explain. Oh, yeah, I see that we have a problem in a camera. So hold on. So let me, why is that, by the way, changing this setting so severely? Hold on. Here. Not this. No. No, this is the way to go. A bit smaller. This one. Okay. now it's okay. I think that I still have to start using the camera that is in my desk, my laptop. It would be so nice to use this other camera because the quality wise is so much better, and when I'm writing it's not shaking. But anyway, so back to this question. Why is that I'm using this sine function? What is that I have here under the square root is that I have apps. Why is that I'm placed apps here under the square root? So, well, that's simply because I don't want to deal with the numbers that are negative values under the square root. So that's the reason that I'm using this sine function. And really my equation is this. The equation that I wanted to use is a flow rate is the semi-empirical parameter multiplied by square root of pressure difference. And now, because the flow can travel two different directions, it can travel this direction as it is shown, and if that's the case, there's no problem whatsoever. But in hydraulics, the flow can have another direction. It can be this direction. And if that's the direction, then the P2 is bigger than the P1. And if P2 is bigger than the P1, we end up to have a negative value under the square root. So there's going to be minus something. I don't want to have any minus number under the square root because I don't want to deal with the imaginary numbers. So that's why I want to have an apps here, which is always converting this value under the square root to be positive. But because the actual direction can change, that will be accounted by using this sine function. Sine function is 1 or minus 1. Minus 1 means that it's traveling from right to left, not left to right. Okay, any other comments, any other questions? Or should we just go? Maybe we'll simply go. Now we're going to take a look at the direction valve, and in the direction valve, I'm going to discuss shortly about digital hydraulics. Digital hydraulics, how that is, the innovation, pretty much the recent innovation in the hydraulics, still research-wise, a little bit underway, but I think it is coming soon. Particularly when you can use that as a pump, that makes quite a bit of sense. Okay, direction valve. So direction valve. Okay, there's another comment. So let me take a look at this other comment, and then I'm going to move. Okay, so if sine. Okay, so if x is less than, so let me go back to here. So if x is less than, oh, hold on, I press something with my sleeves. So when x is less than 0, then this sine function is going to give you minus 1. So it should be okay. Yep. So I guess it is okay. So guys, I think that you are teaching each other. And that's something that is very highly appreciated. So I guess it is okay. And if not, we can continue with this in team session. So, okay, how is the direction valves then? Here's a direction valve that has a two operation conditions. So either it connects pressure port to port A and the tank port to port P, or another way around. So those are the two options. This is how it looks physically. And it's operated by a mechanical shaft, mechanical stick. This kind of mechanical controls are, well, you can still find in tractors, not tractors really, but some trucks. Maybe, some of these lifters you can find very much in the bottom of the trucks. They may be operated by using these mechanical sticks. That's pretty much it. Other than that, you really don't find this kind of systems anymore. Now what happens in today's hydraulics is that this spool that you're moving back and forth, this one here, is very often controlled by magnets. So that's how it goes. Okay, so the one that is here in the middle, that is a land of the spool, and the land is covering these boards. And when it's covering these boards, that's how it is operated. Okay, so if we're going to have, hypothetically, this kind of direction valve. So direction valve, I have here the spool that is the one with the white color This one here is my spool. I need to take my watch off because I keep on touching some of the keyboards here. This is my spool. And then I have the trillings like it is shown here. So I have here pressure, A, B, and a tank. And the question is like, okay, if you can find a direction valve like this, how it looks in real life. I mean, how is a drawing symbol for that? The first one is the one that is shown here. That's not going to be correct. I'm going to give you the answer. This is not in class quiz. So this is not the one shown here because this spool can have a middle position when there is no flow, theoretically no flow whatsoever. So it has to be this one because in the middle session, when the spool is in the middle, there is no flow at all. And when I'm moving to this operation condition, meaning that I'm pushing my spool to positive direction, then the pressure will be connected to A. Now I think that I need to take some of the drawings off to make this more clear. Okay, so when I'm pushing this to positive direction, this is where the positive direction is measured, then the P will be connected to A port. What happens here is that the B will be connected to tank. And when I'm moving the spool to this direction, then the pressure will be connected here, and this guy will be connected here. So these are the three operation conditions, and this is, oh, hold on, so that's not the right drawing symbol. This is the right drawing symbol. In the middle, of course, I'm assuming that this land is exactly the same size as the trillings, and I'm assuming that there is no leakage. In real life, there's a certain amount of leakage that travels through this corner, and it means that it's not necessarily standing still even when you put this in a middle position like this. But the drawing symbol for this is shown like here. Okay, so here are some few examples, and this is there are differences in each other in terms of how big is the land here. So if the land is very small, so it's unable to cover any of the trillings in the middle position, then the drawing symbol look like this. And this is the one we just looked at here. This is going to be the same, but characteristic curve will be very different. And now that's what we need. Again, this characteristic curve is what we need when we're building models of direction valve. So that's why this lengthy discussion about that. Characteristic curve, what is it? It's about how is a relation between the valve opening and the flow rate. The one we look at in the very beginning, the characteristic curve could be something like this. So it's a linear relation between the valve opening and the flow rate. That could be the case. If the lands are significantly bigger than the trillings, then what happens in the very beginning when you started to open the valve is that there is no flow rate whatsoever. And it takes a little while to travel this point here. Once you reach this point, then it could be linear relation. Often, relation between the valve opening and the flow rate is proportional, such that when you're opening the valve a little bit, the flow rate is very minimal. But when you keep on increasing the opening, the flow rate increases progressively. So this is something that the relationship is nonlinear. This is very good when you are using, say, cranes. Cranes, every now and then you have to have a good speed, good high-speed operation condition, and that's when you have the full opening in your valve. So then you can move from one location to another with maximum speed. But on the other hand, every now and then you need some good accuracy in the positioning. And if you have this kind of linear relation, it becomes a little difficult to do that. So this proportional relation helps to do the positioning when the valve opening is small. This is very typical. This is what you can see quite a bit on mobile applications. Okay, but let's moving on and let's see how are the models then. Here's, from this on, I'm going to discuss about valves that are magnetically operated. So only the ones that are kind of like modern valves. The modern valves are the ones that where the spool motion here is controlled by magnets. First thing to do in the modeling is to figure it out how is the spool position. And the spool position follows the input signal with a certain delay. Certain delay because mass of the spool and physics cannot allow the spool to jump from one location to another. Control signal itself can be looking like this. So if I have here a time, this is a control signal. So it may be 0 and then maybe it can jump another value with the 1 instant like shown here. Spool cannot do this. Spool cannot follow. They cannot be here and then fully open with the same right after that when the signal is jumping. So the spool cannot jump because of the inertia. And because of the inertia and because of there's no infinite force to make this motion, this is going to be introducing certain delay. So the spool will follow this kind of control signal with this delay. Okay, this delay may not be that significant, but this is actual spool motion, and the red one again is a spool control signal, the one that is leaving from the control algorithms or joystick or whatever is the means that you're controlling your hydraulics. How fast this can happen, how fast it can move from one location to another location. That is defined by time constant, which is tau here. Tau is a time constant. This is control signal that is coming into this direction valve. And then this is a U dot, so which is a physical representation of spool position. Then you need to wake up. I know that they've been lengthy, maybe a little bit boring lecture today, but wake up and come back to follow me because there's going to be in-class quiz in a minute. A little more than a minute. Anyways, I'm going to ask in my in-class quiz, what is a physical interpretation of this equation? This equation represents spool position. Keep that in your mind. I'm going to put the socrative on. So those ones that are following my discussion can enter their answer. Okay, so it says the physical interpretation of the equation below. Let me show it to you. Got lost. Here. Here it is. Physical interpretation of the equation below. Pressure drop due to a valve, flow through a valve, spool position, numbers of boards in valve. One only is correct. Oh yeah, I see that the answers are coming, so let me move back here. No, it's not going to be 100% here. Where is that you can get this tau, this time constant, that tells how fast valve can move from one location to another. This is a good example about the semi-empirical modeling approach. This one comes from manufacturer's catalog. Manufacturer's catalog are providing something that is called border diagram. Border diagram is made by using experiment, such the way that you're controlling your valve using sine. This kind of function where you kind of forcing valve to be fully open and fully closed. So you're moving your spool to one extreme to another. What you're doing in this curve, in this border diagram, is that you keep on increasing the frequency. Okay, this is not clear picture, but you keep on increasing the frequency like this. And some point, spool is unable to follow this high frequency because the frequency initially is low and then is progressively increasing. And then you look from this border diagram, when the valve is no longer able to follow the signal, that's where you're going to get this time constant. How you can make it happen in real life, we will take a look at the example in a second. Okay, semi-empirical modeling. We're simply going to have the model like this. So we have flow rate. We are assuming the flow to be turbulent flow, so that's why the pressure difference is under the square root. We have here semi-empirical parameter that tells size of the valve. And then we have here spool position. Spool position comes here. The one, remember there is this equation U dot, so on and so forth. That's the one that is integrated, and the integration solution comes here. That's it. That's how it is. Let's take a look at I'm going to go back to the in-class quiz in a second, but this is how valve models look like. Now, depending on the spool position, you have three different scenarios. So if a spool position is positive, this is the way how different ports are connected, and this tells you how is a flow rate traveling through your valve, A and B. And then when it is closed, zero is assumed to be that there's no flow whatsoever, and negative, then the A is connected to tank, B is connected to pressure, and this is how you can compare the flow rates. That's how it goes. Now let me move back to my, oh yeah, I see that we pretty much done with the in-class quiz here. And the game is on. Game is on. Let me put this back. Here we are missing 4 students, so not much. 4 students only. Let me go and get some water, and I will be back with you momentarily. No, I still have a little bit of coffee. Is it getting too late to drink coffee? Kind of, because it's 5:30. Okay, so let me see if I'm still missing somebody. Still, those 4 students are not sure what to answer here. Yeah, but there are a point that is too late to drink coffee, and that's when you become old like me. So you need to be careful with that. So you cannot live in itch. Okay, 2 students are still thinking, so momentarily we will go. So I guess that I will show the success rate. So my personal guess, I will stay with my previous number. So it's going to be 74. 74. And here it is. The correct answer is, okay, not bad, 88. 88. 88. So this equation, naturally, what like I was repeating number of times, it is describing the spool position. It's a little bit confusing, perhaps, because we're speaking about like voltage, but physical interpretation is a spool position. This is a first order delay equation which describes inertia. Inertia, and it's another example about the semi-empirical modeling, because to make the physics-based model about the spool position, you should know inertia, properties, friction, and so on and so forth. It becomes to be very, very difficult. Okay, but let me see how is a game today. So I got the, is it that we got the same winner than in the previous time? 80, we don't have 88 here, or do we? No, we don't. 80, 88. We got 89. I think that's acceptable. 89 is acceptable. Uh, Here. And what else? What are the other good cases? That's about it. Okay. You said that there's 88. I don't see your answer here as an 88. Why is it somewhere here? Huh. Okay, I need to check that a bit later. So, anyways, let's move on to final item for today's lecture. The final thing for today's lecture is okay. I see that I have digital hydraulics, and then we can move on to cylinder modeling. Okay, digital hydraulics. I have a very nice YouTube site. Is this one here? I will try to play the YouTube. I don't think I think it is not going to be possible to do it because what will happen is that I will hear the discussion from the YouTube, but you don't hear it. And you need to hear it by yourself because otherwise you don't get the concept of digital hydraulics. Shortly, let me first explain it to you, and then later I'm encouraging you to check this YouTube because this could be something that I'm asking in midterm exam. What is a deal with digital hydraulics? Well, digital hydraulics is replacing conventional valves that are based on the motion of the spool by number of on-off valves. On-off valves. And that's where the name digital is coming from. Because these on-off valves are either fully closed or fully open. And of course, the one valve is not doing the job because, the flow, again, characteristic curve of the valve that is based on the spool motion is something like, let me put it the other way around. Let me check this off. Okay, so if this is a flow rate and if this is a valve opening, let's put it like this way, it's could be something like this. So you can get a lot of different kind of flows. And now if you have just one on-off valve, you get the very discrete value. So you get the one value and that's it. But if you get two, you can get more values. And if you get three, you can get the combination. These valves can have a difference in size. And once they have a difference in size, then you can start to have more and more variables and more positions that can be controlled by these on-off valves. So you put these valves parallel as it is shown here, and then you keep on opening them in a different ways. And based on the way you're opening that, you can get kind of this characteristic curve. It is mentioned that digital hydraulics is good because then you can get rid of this control based on the pressure differences. That's not entirely true. That's not exactly the case, but there is some huge potential related to this, particularly if you can control the pump using the same concept than valves. And it means that in a pump wise, which is typically the piston pump, you make a decision every time the piston is moving, whether or not you're producing energy to the system. And that's something that would be very nice energy-wise. And the energy is a big deal today. So we need to get back to this digital hydraulics when we are discussing about the pumps. But shortly, again, idea is that this kind of continuous analogical valve, if you may, where the spool is moving back and forth, is replaced by a number of on-off valves. And they have a number of different combination of opening and closing options. And based on those kind of number of opening options, you get the number of different points in these characteristic curves. And once you have enough points, it resembles analytical valve. And the benefit is that you can get, that it's mentioned that the maintenance-wise is better solution and energy-wise is a better solution. Take a look at the video and make your conclusion by yourself, but make sure you understand the concept behind the digital hydraulics, because I might ask that in next midterm exam. So let's take a look at an example. So in this example, I have here screenshots from the manufacturer's catalog. And the first screenshot I have is a characteristic curve. So I have here valve opening and the flow rate. percentage-wise. And now this is, we need to change the color to make this more visible. You see that this characteristic curve is pretty much like was shown in one of the slides in the beginning of today's lecture. So valve opening and flow rate are linearly related. So this is going to be exactly the model that can be modeled by using this equation. Well, this equation, when you take Q on another side of the equation, that's how it is. So Q is equal then the semi-empirical parameter, valve position, and the pressure difference under the skew. This characteristic curve was actually mentioned that the nominal flow in a full opening is 24 liters per minute when the pressure difference is 35 bars. These are the values directly obtained from the manufacturer's catalog. So first thing is this semi-empirical parameter. This one here, the laminar flow, nominal flow, is substituted here with the full opening, and full opening is assumed to be 10 voltage here. That's where the 10 is coming. And the pressure difference goes under the skew bar, under the skew root, and is this one here, 35 bars. That's going to be your semi-empirical parameter. And the next, or the final step to do is this Bode diagram. This Bode diagram is made exactly like I mentioned earlier. So you're controlling the spool position using this kind of a sine function. And the first assigned frequency is very low, as then it started to increase like this, like that. This tells you what happens when you increase in the frequency. And as you see here, when the frequency is 10 Hertz, then there's no difference regarding the spool position and control signal is 1-to-1. There started to be a little bit of difference when it is 20 Hertz, particularly when it has a full opening. So this is 100% opening. This is a 5% opening. So 5% opening is just a moving spool a little bit back and forth in the middle. So here, this is 100% opening, some difference in 20 Hertz, some more significant differences when there's 35 Hertz. This is when the phase becomes to be here, that the difference between the signal and spool position becomes to be 45 angle. And this is when I'm going to take this speed of the valve. This is the value that I'm getting. This one goes here. And this is the one that I'm using in my differential equation to estimate the spool position. Okay. Oh, this is not looking very good. So let me make it all right, like this. Pressure relief valve. There is a lecture material. So you can take a look at the lecture material. This is going to be a reading assignment. So I'm going to just briefly explain it to you, and then I'm going to close for today. So, pressure relief valve, that's what we looked in the very beginning. That's a painful component because it's based on so many different parameters. And how it behaves analytically is this equation. Now, this equation is the flow through this valve. But the first, you need to know the spool position. Spool position, which will be extremely difficult to get. This can be obtained by using this physics-based equation. I have here pressure forces, flow forces, spring forces, mass of the spool, so on and so forth. So this is going to be quite a bit of, okay, I think there's a flow force to be this pretension of the flow force. This should be this guy here. There's a typing mistake here. To get solution from this equation will be too much to ask. So what will happen again is that these combination of equations will be converted to be in a semi-empirical form. And that's the form you can get these unknown parameters from the manufacturer's catalog. So that's what it is, shortly speaking. How it happens, how it looked once you do this manipulation, it looked like this. So you get the parameters, which the K here is a representation of spool position, and the parameters you need is C1, C2, and C dyne. So you need 3 parameters instead of the number of parameters mentioned earlier. And these parameters you can get again from the manufacturer's catalog. So it makes quite a bit of sense to use this approach. Now, what follows is that there are 2 remaining components to discuss: cylinder and a pump. And we'll get back to cylinder and a pump next Monday. So we're going to spend a little bit of time for the cylinder, a little bit of time for the pump, and then we're done with the hydraulics. And then I'm going to explain a little bit about something that is called flexible multibody dynamics. And as the title implies, it is a method to describe mechanical flexibility. I don't know if you care about this, but if you look at my publication, most of my publications are in the field of flexible multibody dynamics, meaning that we're speaking about systems where the bodies are connected together via joints, but bodies can experience mechanical deformation. How those can be modeled, that I will explain to you on next Monday. So I see that I spent an hour and a half, so it's pretty much time to close today. And remember this, my green screen is in mail, so next Monday, hopefully if everything goes fine as planned, it's going to be something that you will be amazed. You will be amazed. So I'm going to take, I'm going to make like my YouTube channel to be something that is extremely nice. Flexible multibody dynamics and the green screen and other surprises. What are those surprises? Stay tuned. Come back on Monday. And with that, I'm going to close today's lecture and I will move on to Teams. Any additional comments, anything, see me in the Teams after a little bit. Okay, so on next Monday.